Okay, we've talked about taking the derivative of a sum of terms, which could be functions. We've talked about taking the derivative of a product or a quotient of two functions, and we realized that we must do something a little bit more than you would expect on those. You have to do the product rule or the quotient rule. In other words, the derivative of f times g is not just f prime g prime as we would love it to be. We have to do the work behind the scenes on that one. And now I want to talk about taking the derivative of a composite function. Now, a composite function is a function that sits inside of another function. So, for example, if we had a function that was x squared, and we had a function over here that was x plus 3. Now, I could do a number of things with them. I could multiply them, I could add them, but how do you get one function to live inside the other? That's a composite function. Well, here's x squared. I'm going to take x plus 3 and put that into my x, and now I have x plus 3 all squared. That's a composite function. You don't multiply them, you don't add them, you actually put one function inside of the other. Now, in order to understand the connection, the relationship between the derivatives of these composite functions, I want to give you a little diagram that I put together here, and you can make fun of my pictures of my gears because I'm not really good at drawing these gears. But if you look at example 1 in the book, it is a superb example of seeing how two functions work cooperatively together as composite functions. One works after the other, and that's generally how it works when you use composite functions. And primarily, I want to look at the rates of change because derivatives are rates of change. So how does the rate of change of the first function and the second function combine together to give me the overall rate of change? So let's take a look at that. So this is section 2.4, the chain rule. Now, if you do look at that diagram, and it's going to be a lot better than mine, what I see are gears. And the first gear is this small little gear here with a little handle on it. And your job will be to turn that handle. Okay? So we're going to turn the handle counterclockwise, and we're going to make this second gear move because there's a connection in here. Now, I will tell you there's a 3-to-1 gear ratio, so you can imagine that if you crank this handle 3 times, you're going to get this big gear to turn around once in its entirety. Now, let's talk about the mathematical relationship here. This I've labeled as y revolutions per minute, and that's you turning the handle. This axle right here that comes out of the center of this gear will start turning at u revolutions per minute. Which one's faster? Which one's slower? Think about it. So you're turning the little gear, and you actually got to turn it a number of times before you get the big gear to even turn once. So I'm imagining that this is going to be turning faster, and this is going to be turning slower. How do we relate that to a derivative? My question is, how does y change with respect to u? And guess what? That's a derivative, isn't it? dy du. So derivatives are rates of change, and we read these as how does this change with respect to that? Well, if that's a 3-to-1 gear ratio, I need 3 turns in y to get me 1 turn in u. So dy du would be 3. So derivatives are rates of change, and in this case, I need 3 turns to get me 1 turn. So dy du would be 3. 3 changes in y get me 1 change in u. Now the u gear is connected to another one, and that's down here. So gear 2 has an axle that comes out of it and is connected to a small gear 3. So these are related. This is connected right here. So these turn at the same rate. Gear 2 and 3 are turning at the same rate right now. Gear 3 is connected to gear 4. Again, they're connected, but one is bigger. And in fact, the gear ratio on that is going to be 2-to-1. And now I have a question. And the question is, how many turns would you need to make on this little gear to get 1 change or one turn in this gear? Well, again, because the gear ratios are 2 to 1, I imagine that it takes 2 turns here, 1, 2 turns, to get this gear to turn around a full cycle. That would seem to be another derivative. How does u change with respect to how x changes, du dx? Well, I need 2 turns or 2 changes in u to get me 1 turn or 1 change in x. Du dx is equal to 2. So we've already done some derivatives on this. Derivatives are rates of change. How does one variable change with respect to the other? In this case, this is turning with speed u. This is turning with speed x. And so du dx would be du, 2 changes in u, get me 1 change in x. So du dx would be 2. Now the real question is the big picture, and that is, how many turns will it take on gear 1, and of course that's where we're revolving it at y revolutions per minute, will it take to get me 1 turn on gear 4, and that's x revolutions per minute. So you're up here at handle 1, and you're cranking this along counterclockwise, and my question is, how many turns is it going to take for you to get this gear to move just 1 time? Now think it through. 3 turns here, 1, 2, 3, get me 1 turn here, which also gets me 1 turn here. That's not enough. I need 2 turns here. So another 3 cranks, 1, 2, 3, gets my 2nd turn and makes this one turn 1 full cycle. So the answer is going to be 6. But how do we relate that to derivatives? What you really want is dy dx in this problem. Why would that be dy dx? Well, take a look at the picture. How many changes in y will it take to get you a change in x? Dy dx. And the chain rule works like this. You chain derivatives together. So you would take the dy du derivative and you simply multiply it by du dx. Now, why does that work? Well, it certainly works for this problem because dy du was computed to be 3, du dx is computed to be 2, and so 3 times 2 does make 6. You can also imagine that the du's cancel. So it's a good connection between those different rates of change. So let's talk about the chain rule. This is really one form of the chain rule right here. And where's the u, the y, the x in a math problem? Well, you could have a function that looks like this. Instead of just putting an x into the f function, you're actually sticking another function into the function. And that's called the composite function. So that's f of u of x. So what would that look like? How about the example I gave you earlier? X plus 3 squared. Now, the primary function, f of x, the outer function, is a squaring function. The inner function is just x plus 3. So if we composite these together, it looks like this. Now, I like to composite functions by working with the outer function. Now, the outer function is an f function. It says all I do is square things. No matter what you stick in here, I square it. So you gave me this u of x thing. I am going to square that because that's my job as an f function. F functions square stuff. But u of x is known. It's right there. So it's x plus 3 squared. Now, because it's x plus 3 squared, we can do some algebra on that, right? And not only can we do the algebra, we can do our derivative, dy dx. We don't need any special rule for that. So we've got our dy dx right there. So really, no matter what we do here, we have to make sure that dy dx comes out to be 2x plus 6. Let's see if the chain rule really works. Now, the chain rule says you've got a composite function. You've got, and we could call this, I suppose, f of u equals u squared, or y equals u squared. And we have another function, which is u itself. And u of x is x plus 3. So we're using a dummy variable here for this. We're using the dummy variable u instead of x for that function. Now, the chain rule says that if you were to composite these together, in other words, if you really were to put this in here, your f of u becomes, or another way to do this is to just replace the letter u with all of that. So it truly is the same function. Just checking. And therefore, f prime better be 2x plus 6. Here's what the chain rule says. The chain rule says if you have a function defined like separately like this, and you can see both components very clearly, and you really want to know what would happen if you put them together, what would the rates of change be when they combine? Chain rule says do it this way. dy du multiplied by du dx. Guys, let's try that. Now, dy du is right here. dy du. Take the derivative with respect to the independent variable. There are no x's up here. There's only u's. So it's going to be a 2u, just like it would be a 2x if we did it with respect to x. Now, du dx couldn't be easier. That's the derivative of x, which is just 1. And so the derivative of the two functions working together as a composite function is 2u, which does not match the correct derivative with respect to x up here. I guess what we need to do is plug u in. And u happens to be x plus 3. Out it comes. So here's how it works. You want to take the derivative of the u, the lonely inner function, all by itself. You want to take the derivative of the outer function, all by itself. And somehow they get combined together. There's a shortcut for this. Now, what's going on here, rather than use the u, let's do it this way. Let's do the f of g of x. F is the outer function. It does things like square, cube, sine, cosine, anything like that. And g of x is the inner function, which could be, again, any kind of function. What happens is the following. Remember, you get two derivatives, right? You end up getting f prime, and in fact, there's no change to the argument when you do your f prime. And then you just do g prime, which is dg dx, like du dx. It looks like that. How do I apply that to a problem, though? Let's apply it to this one. Forget looking at both functions separately, I guess. Let's put them all together. So my function is going to look like this. My outer function, like if I just cover this up, my outer function is a squaring function. My inner function is just x plus 3. So the way to do this, f prime times g prime, is just take the derivative of the outer function. In fact, this really should be a u. Take the derivative of the outer function. So how would you take the derivative of a squared function? Well, if it were just u squared, the derivative would be 2u. So the 2 would drop down. you would deduct 1 from the exponent, and then no change to that argument. It does say g of x right here. And g of x is x plus 3. So you do take the derivative. The derivative of something squared is 2 times that something, but the something doesn't change. It's still g of x itself. So that would be x plus 3. No change to the argument. Times, this is where the chain comes in. This is like the dy du. Now, over here, we get the du dx. Well, it's really dg dx in this case. So there's the g prime, right next to it, multiplication. G prime is equal to 1. And that's actually the chaining part right there. So the quickest way to go about doing this is not actually to use f and g or u. Is to do it directly from the composite function itself. And I want you to deal with the outer function first. Here's another function. Now, if I asked you for the derivative, you would say y prime is equal to, well, derivative. Now, I want you to go to the outer function first. So the derivative of sine is cosine, correct? And the way the chain rule works is when you do that derivative of the outer function, no change to this argument. No change to the argument. So you just do one derivative at a time. So derivative of sine is cosine. Remember this, no change to the argument, so we stick that in there. And then, chain rule is always multiplication. I want you to check off the next function, which is x squared. Okay, what's the derivative of x squared? 2x, and that chain's on the back there. And you're done. That is the correct derivative. So we're going to get 2x times the cosine of x squared. 2x times the cosine of x squared. So the fact of the matter is this. We have what's also called the general power rule, because oftentimes the composite function is consisting of a power function as the outer function. Remember, when you do your chain rule, we always do the outer function first. So let's say we had some function in here raised to the nth power. That's really two functions. There's an inner here and an outer out here. The general power rule says the following. Do the power rule, y prime. The n will drop out in front, as it always does. Always deduct 1 from that exponent. And I'll say this often, no change to the argument. If you're changing that argument, you're doing too much too fast. Now, I often check things off when I take their derivative, so I'll check off the n, the nth power, because I took its derivative. But the chain rule says, hold on, you got to do one more derivative, and that would be the derivative of that function. And whatever that is, that'd be g prime that hangs on the backside. Let me give you an example of using the general power rule. So what if my function, and now we can just call it f of x, and we're not going to piece out the two inner and outer functions as named functions. This f of x is going to be the entire composite function. And what if f of x was this? Like this. General power rule. If the outer function is a power, run the general power rule. How you do that is you check it off, because I'm about to take its derivative. Here comes f prime. The 2, like any other power derivative, drops out front. You deduct 1 from the exponent, and I will say this often, no change to the argument, please. If you change the argument, again, you're going a little too fast. Slow it down, one derivative at a time. Take the derivative of squared. That's 2 comes down, deduct 1, copy the contents. Now we chain off the next derivative, which would be derivative x cubed plus 1 is 3x squared. So what is our derivative here? Let's piece it together to see what we have. 3 times 2 is 6x squared multiplied by x cubed plus 1 to the 1 power, distributive law. That would be 6x to the 5th power plus 6x squared. Now this happens to be an example we can actually check, and I really do want to check this. Sometimes you can avoid doing the chain rule if you can just square or cube it out. In other words, if you can just multiply and spell it out, that might help you avoid running the chain rule. But you can always run the chain rule. You can see and get the right answer. So let's try it without the chain rule. This happens to be an example where I can do this without the chain rule. Start over. This was x cubed plus 1 squared. Oh, binomial squared. We have a shortcut for that. We take the first item and square it. We take the last item and square it. And then don't forget one of each for the middle term. 2x cubed times 1 is 2x cubed. Got that? What do you do with exponents in a diagonal line like that? You multiply them. So this is just algebra, no calculus. And now, you don't need a chain rule. You don't need a product rule. In fact, f prime is just the derivative of power functions. The derivative of x to the 6th, the 6 comes down, is 6, and then deduct 1 from the exponent, plus the 2 is a constant multiple. That's not going anywhere. That's along for the ride. The 3, though, comes down, and you deduct 1 from the exponent. So what is the derivative without running the chain rule? Exactly what we got earlier. There it is. So it's pretty cool when you do a math problem two entirely different ways and get the same result. I mean, that's a pretty strong indication that you got it right. What happens if we have a function that has some radicals in it? What do we do then? Here's a function that we're now empowered to take the derivative of. One of the things you want to do in calculus is you want to get away from radicals. You want to get away from them because you want to write them for what they are. They are exponents. That's a great way to write a radical. In fact, this is a cube root. We don't really deal with radicals when we're taking derivatives. We like to see exponents, and there it is right there. So in reality, what is this? This is just the general power rule, apparently. So run the power rule on the outer function, and then run the derivative chain rule on the inner function. But do this one first, and I like to check these off. So let's do f prime. Check off the 1/3. The 1/3 drops down. Parentheses, deduct 1 from the exponent. And that's how you deduct 1 from the exponent, minus 1. Oh, remember this. I say it often. No change to the argument, please. If you make a change here, it's going too fast. It's not supposed to change. Now, chain rule dictates that we take the derivative of just what's inside, which is 2x. Let's see what we got here. We got a 2x on top. We got a 3 on the bottom. Even this belongs on the bottom. It's a negative exponent, which is x squared plus 1 to the 2/3 power. Now, if I said put this in simplest radical form, you should be able to do that by changing this back to a radical. This is a cube root. That's what the 3 is doing here. And the squared is an exponent, like that. Now, wouldn't it be nice if that was a cube? Because if that was a cube root of a cube cancels out. Can we make that happen? We sure can. We don't like radicals in the bottom, and I think if you just put one of these inside the cube root, just one, that's going to be plenty enough to get at the radical out from that denominator. So let's see what we got on top here. Simplest radical form, 2x, cube root of x squared plus 1, 3, oh, and look what happened, guys. X squared plus 1 squared, x squared plus 1 to the 1, precisely what I wanted. X squared plus 1 cubed. So what do we actually have in the end here? Well, the cube root on the top isn't going anywhere. We're stuck with it. But cube root and a cube cancel out. So I guess we could finalize this as 2x, and it's a cube root of x squared plus 1 on top. and a 3x squared plus 3 on the bottom, and that is the derivative in simplest radical form. So really, if you think about what a radical is, it's nothing more than a fancy exponent. Run the general power rule. Now, the next thing I'd like to try is I want to differentiate some quotients. So let's break out our differentiation verb, d dx. So my question is, do we need the quotient rule? Quotient rule is f prime g minus fg prime all over g squared. That's going to work for this problem, but it's overkill. Here's why it's overkill. Can't I just bring this to the top? If there's a constant up there like that, I think we can just bring it up. And if we bring it up, it's no longer really a quotient. Run your general power rule. The derivative of a minus 4 exponent, we know what happens. The minus 4 comes out front. We deduct 1 from the exponent carefully here. And I've said it many times before, but I'll say it again. No change to that argument, please. No change to the argument. When you're working with the outer function, do not touch the inner function. All right, chain rule says, hey, one more check mark. You check this off. You didn't check this off yet. Now you can check it off. So what's the final derivative here? Well, there's a minus 8x on the top, and there's an x squared minus 1 to the 5th power on the bottom. So oftentimes, there are derivatives where you don't have to run the quotient rule, thankfully. And that was certainly one of those situations. All right, now I'm going to finish up. I have 2 more examples to do, one of which is the derivative where you do have to run a quotient rule, something like this. Naturally, that's going to be some extra work. I don't believe that you're going to be able to square this out and cancel. I mean, these are already the factors. So I would just call this F. I would call that G, and you're going to have to make a table. This is good review for the quotient rule. So when you make your table, you put your F here, you put your G there, and you must now take derivatives of each. But wait a second. This is a composite function. So how do you do this? You take the derivative of the outer, that would be a 2 comes down, deduct 1, copy what's inside, no change, and then don't forget one more derivative of the inner, and that'll be 4x. So actually this is 8x, 2x squared plus 1, or you could even say it's 16x cubed plus 8x if you want. G prime. Take off the 3 because that's your cube function. We take the 3 down, deduct 1 from the exponent. Remember, always copy what's inside. But one more derivative. Oh, let me change this. I made a mistake, so I'll do it up here. Make this 2x squared. Sorry about that, because I made that 2x squared. So 2x squared plus 1 is now our f. But 3x minus 1 cubed, right? So the 3 came down, I deducted 1. I checked off this. The derivative of 3x is simply 3. So g prime is now 9 times 3x minus 1 squared. Might as well spell it out, see what it is. It is 9x squared minus 6x plus 1. And we can go a little bit further here. That's 81x squared minus 54x plus 9. There it is all spelled out. All right. That was all chain rule. There were 2 of them, one for F and one for G. And it's what I've been doing all along. Derivative of the outer, no change to the argument, times the derivative of the inner next to it. The real problem on this guy is going to be all of this. Because I really have to run the quotient rule on this. So f prime g minus f times g prime all over g squared. So what I did is I squared g. When you square that, you get 3 times 2 is 6. Wow, that is just a lot of stuff up there. Now, you might find that if you had left it in factored form, there might be some opportunities to do some canceling here. Let me revisit this by leaving it in factored form. See, f prime is 8x 2x squared plus 1. G is right there, 3x minus 1 cubed. A little cleaner, isn't it? Minus f, that's 2x squared plus 1 squared times g prime. Let's use this version of g prime right here. All over g squared. I think this is better, guys, and the reason I think it's better is because, look at this. 3x minus 1 shows up all over the place. In fact, there's a common 3x minus 1 squared that can come out front. Let's rip the 3x minus 1 squared common factor out front. And look what's underneath. And show me what's left. Well, this will be 8x, 2x squared plus 1. One of them is left because I've only taken 2 of them out front here. So they'll have one of these. And over here, the 3x minus 1 squared, the whole package came out front. So I'm going to be left with a minus 9 times 2x squared plus 1 squared. So the most important thing to know here is there is definitely going to be some cancellation here. So I'm going to get on top 8x times 6x cubed minus 2x squared plus 3x minus 1. Close that off. And I'm going to get a minus 9, and I got to square that binomial, 4x to the 4th, 4x squared plus 1, and I'll deal with that in a moment. But 2 of these canceled with 2 of these, leaving 4 behind. And you will find that will happen on a quotient rule problem often. Well, unfortunately, we're not done because we have more work to do up here. 48x to the 4th, 16x cubed, 24x's minus 8x squared. Sorry, that should be squared. And then this is minus 36x to the 4th, minus 36x squared, and minus 9 all over this. Boy, there was a lot of work to do here, but it was chain rule and quotient rule. How many x to the 4th do we really have? It looks like there's only 12 left. How many x cubes do we have? Well, those are the only x cubes I've got. How many x squareds do I have? 24, but I take 36 of them away. How many x's do I have? And how many numbers? So I think that's as far as we can go with this here. So clearly, a quotient, much more involved. And in fact, when the chain rule is involved, we got a lot of work to do all around. So I'm trying to focus on the chain rule, and then, of course, we got into that quotient rule pretty deeply, but also a very good example of the quotient rule. So if you're doing a quotient rule, you need f prime, you need g prime. Don't forget to run your chain rule. Now, the last thing I'm going to leave you with, I'm going to do a trig chain rule by taking the derivative of the, let's say, the sine of 4x to the 4th power. The way we do this is we check off sine and we write down what it is. The derivative of sine is cosine. You know what I keep saying. No change to that argument. Don't go too fast. Chain off another derivative, which would be 16x cubed. I kind of like this up front. So this would be the derivative right here. You know that things outside the parentheses don't interact with the things inside. Let's try something else. d dx, the tangent of the sine of x cubed. This is a very good example of the chain rule running multiple times. Start with your outer function. Who remembers the derivative of tangent? Might be one you have to look up, but it is one that I expect that you know. The derivative of tangent ends up being secant squared. Of what? Oh, that's right. No change to the entire argument. No change at all. Okay, let's keep going. Chain rule. The next chain, dot, you take the derivative of sine, which is cosine. And what do we put inside the cosine? No change to its argument. One more dot. The derivative of x cubed is 3x squared, and I think we're finally done with this derivative. We've got them all. Now, I like the 3x squared. I prefer that to be up front. And I guess the order here, I put the cosine up front most likely. See how it's kind of getting more complicated as we go, and then secant squared of the sine of x cubed. So this example shows you a couple things. It shows you not only how to do multiple chain rules, but also how to deal with trig functions. All right, one last one. We'll leave you with that. This video is going a little bit too long here, but I do want you to know how to do this. One last problem, and I'm going to really put a lot of stuff in here. Let's take the derivative of the sine of the tangent of 3x plus 2 cubed. That's going to be a bit of work. Let's work it out, guys. All you have to do is check things off. Check off your sign. What's the derivative of sine? Cosine. What do you put inside of it? Whatever you put inside the sign, actually. No change to the argument. I mean the whole thing. The whole thing goes in there. Done. Move on. What's the derivative of tangent? We just discussed this. It's secant squared. And what do you put inside the secant squared? Whatever was in the tangent. The whole thing. Next. What's the next function in line? This power right here. Check it off. The 3 comes down, and you deduct 1 from the argument. So you deduct 1 from the exponent, sorry. No change to its little argument, which is 3x plus 2. And boy, we got one more to go. That's this one here. The inner function is 3x plus 2. The derivative is 3. So how would I finish this up? Well, 3 times 3 is 9. And then maybe you could put 3x plus 2 squared next. And then, I mean, these are equally more, I guess maybe that one might be next. I like to make it more complicated as you get to the back here. And then the final one is a cosine of a tangent of 3x plus 2 cubed. Now, note that this is cosine of tangent. That's not cosine times tangent. If it were cosine of theta times the tangent of theta, the answer for that is sine. The cosine of theta times the tangent of theta is sine. Why is that? Because tangent is sine over cosine. The cosines would cancel. Can't do that here. You cannot cancel because it's not cosine times, it's cosine of. So really, there's no way to cancel those. So you've seen the chain rule used pretty deeply on a multiple levels here. And you know how to do it, hopefully. You check off one function, the outer function. You work on that. Don't change the argument. Then check off the next one. Take the derivative of that. Don't change its argument. And then just keep digging your way in until finally you get to the last inner function. Sometimes the last inner function is just the letter x. That's okay. You can take the derivative of that too. The derivative of x is 1. And that would be the last thing at the end of your chain rule. Okay, that's it. Sorry I went so long, but I definitely wanted you to really see how to do the chain rule, and I think we've covered quite a bit. Please do the homework problems. That's the best way to get your experience in actually doing the chain rule. Thanks, everyone.